So what is noise margin? Noise margin is actually defined as how much noise a gate input can receive before it starts to cause the signal to distort. So for example, if you have an input over here, right? If it's an inverter, you should invert the signal, and when it goes to another inverter, it will invert again. But if the signal is distorted, for example, if it's like this, sometimes it cannot read the signal, so it will also produce a distortion instead of an inversion. So all this output depends on the noise margin. So what we want to do is to have a very good noise margin. That means a wide input range, and produce a distinct output range. So if you can see here, this diagram is the output voltage range. Here, this is the output, and this is the input. The y-axis is the voltage level. So if you look here on the right at the input range, so this is all the input that it can accept. So let's say our voltage range is between 0 to 5. So here it is divided into 3. The first region is for the low, and the middle region is the indeterminate region, and the third region is for the high. So if you have a low input, it should produce a high output, and the high input should produce a low output. Okay, so let's see here. So if you have an input range of between 0 to 5, and we want to minimize this indeterminate region. So let's say our range here is 2 volts, and this is 3 volts. So there is only 1 volt which is indeterminate. Other voltage, so for example, if you receive 0, 0.5, 1.5, all of these values, when it goes through the inverter, it will produce a high output. And the same way, any value input between 3 to 5, so 3, 3.5, 4.5, can produce a low output of 0. So the idea is we want to maximize the noise margin at the input so that it will produce a very distinct output. So how do we do that? So when we want to control the noise margin, you can control it by controlling the beta P and the beta N. So the beta P and beta N should be equals to 1 for equal switching, and to maximize noise region, we want the unity, you want the slope to be -1. So this is the voltage transfer characteristic. As you remember from the previous class, this graph can skew to the left if beta P over beta N is less than 1, or skew to the right if beta P over beta N is much greater than 1. So we want it, other than fixing it to be at the center, we also want to control the slope. So we want the slope to be at -1. Okay, so how do we do that? We can do that by controlling the size of the transistor, and we look at which point of the which region is the NMOS and the PMOS. So if you can see here, in the region A, the NMOS is off and the PMOS is in linear. Right, this is in A region, and in region B, the PMOS is in linear and the NMOS is starting to turn on and it is in saturation. C is the midpoint. So when it is in the linear region, the equation for the transistor is this, and when the transistor is in saturation, the equation is this. Okay, so proper sizing will allow the transistor to have equal rise and fall time. Okay, so when you do this, it is hard to always use the equations. So the equations can be quadratic equation or this linear region equation, which is long and complicated. So in order to simplify the calculations, we can use the SPICE simulator. So this can accurately model the IV curve. So simulations are also complex. So if the engineer wants to make a ballpark idea, what they need to do is transform the transistor into an R and C model. So this is the reason why we want to transform the transistor into an RC model, is so that we can find out the delay, or the delay, for example, this is the input, when does the output come out. So the output only comes out at a later point, so there is actually a difference here. This delta t, or the delay between the input and the output, is known as tau, right? And tau is related to R and C of the transistor. Okay.